Hello everyone, my name is Partho Das, Assistant Professor, JS College of Engineering, Department of Electrical Engineering, West Bengal, India. First of all, welcome to my class. So today we are going to do some problems on AC fundamental chapter. So in the previous classes, already we have discussed about the everything about AC circuit. So AC circuit means we know that AC circuit means there we have R, the resistance, A, that is the inductance, and C, that is the capacitance. All properties are present. As in the case of DC circuit, we know that with the DC source, only resistor can work. So there is no such difficulty with dealing with the DC circuit, because in case of DC circuit only we have DC source, maybe voltage, maybe current, and with that we have resistors only. But in case of AC circuit, uh, all components, all electrical parameters can be present over there. Not only resistance, there may be present inductance, capacitance. So those things combining the total property of our AC circuit. So today we are going to solve those kind of circuits. Uh, so let us before starting, so just giving you a preliminary idea. So coming to the next slide. Yes. RLC series circuit. So first, as the name suggested, that uh, in a RLC series circuit, R, that means the resistance, L, that is the inductance, C is the capacitance, all components are connected in series. So as we can see in the diagram, RLC all connected in series, then it is the RLC series circuit. Basically this is the RLC series circuit. Now the point is, there is a term that is impedance. What is impedance? Already we have discussed in the previous classes. What is impedance? Impedance is the total summation of the resistance and the net reactance of inductance and capacitance. Okay, so see what is written over here. A series RLC series a series RLC circuit contains both inductance and capacitance. Yes, it is correct. So L, C both are present, so XL must be over there and XC must be over there. Since inductive reactance and capacitive reactance have opposite effects on the circuit phase angle, the total reactance is less than either individual reactance. That means what it is telling, that the when we have discussed the phasor diagram, the phasor diagram of this inductive property and capacitive property, there we have seen that the relation between voltage and current. So what we have seen over there, in case of inductance, we have seen that from the voltage, current is lagging behind by an angle 90 degree, or vice versa, from the current voltage is leading by an angle 90 degree. Now capacitor in case of capacitor, we have seen that with respect to the voltage, current is leading behind by an angle 90 degree. In case of uh, uh, from the voltage, and reversely we can say that from the current, voltage is lagging behind by an angle 90 degree. So those are the things. So those things already we have discussed. So there we have the, if we have a pure inductive circuit, then, or capacitive circuit, then we have seen that in between voltage and current there is an angle of 90 degree, correct? So using those concepts, we have seen that XL and XC both are the two different components and has two different expression. So what is the expression for XL? XL expression is given by 2 pi FL. So we can say that this inductance is a reactive component. Then Xc, what is Xc? Xc is 1 by 2 pi Fc. So 1 by 2 pi Fc, then it is also a frequency dependent component. But try to understand what is the difference. The difference is, the in case of XL, that is the inductive reactance, there we have seen that the between frequency and inductive reactance the relation is linear. And in case of capacitive reactance, there what we have seen, there we have seen that the relation between frequency and capacitive reactance is reversed. So with respect to the change of the frequency, so the value of the both components is changing opposite direction. So as XL with frequency it is directly proportional, correct, and with XC the frequency is inversely proportional. So what does that mean? That means if we are changing the frequency, that means say we are increasing the frequency. So when we are increasing the frequency, so XL will definitely increase and XC will definitely decrease. And if we want to decrease the frequency, then what will happen? XC is increasing now and XL is decreasing now. So those things will happen. So we can say that the property values are changing in opposite direction. That's why in the last line of this first paragraph it is told that the total reactance is less than either individual reactance, correct. So because we are dealing with the net reactance is the difference between these two. Maybe in any case, maybe XL may be higher or XC may be higher, so anything may be happen, so we doesn't know. So that's why we have to consider both things. So first of all, so for your better understanding, I know these things are already discussed with you in a very short manner in the previous classes. Now we are going to deal with the problems regarding this chapter. So what we have, so for our understanding we have considered R, L and C. So this R, L and C, so we know that resistance doesn't have any inductive property, correct, or reactive capacity property. It doesn't have any leading or lagging capacity. It only makes some voltage drop. And other two components L and C, so it has some reactance value, so it has some leading lagging capacity. So in that case we are dealing with the net reactance value of those. So what is the total impedance value? So total impedance value, so as we go for the next slide, yes, so follow my pointer, the equation number 18.2. So there is, we can see the vector notation. So this is the vector equation. As we can see, Z is equal to R plus JXL minus JXC, where J is the complex conjugate. So now if we want to change this equation, so what we can do, we can convert this like this. So under root R square plus XL minus XC whole square into tan inverse X by R, correct. X is the net reactance, that is when XL minus X is that difference is we are discussing about. So this is the impedance equation. Like this way we have discussed about the phase angle equation, we have discussed the power factor equation, we have discussed the voltage across the different components, resistance, inductance, capacitance. So lots of equations we have already discussed. So now our purpose, just I am giving some recap of the concept that we have done. So now using those concepts we are going to solve different problems. So coming the problem number 1. Yes. So what is the statement of the problem? Determine the total impedance in figure 18 to express it in both rectangular and polar forms. So yes. So first of all, what we have to do, we have to find out total impedance, and we have to express it in which form, in rectangular form, in the polar form. We have discussed this in the previous classes when we have discussed about the theory part of this session. There we have discussed what is rectangular form, what is the polar form. So to find out, to first thing is we have to find out, so our aim is to find out the impedance. So now first, when it is told that that we have to find out the impedance, so what we have to do, first of all we think okay, so we have to find out the impedance. So what is the formula for impedance? So the formula for impedance is Z is equal to under root R square plus XL and XC whole square, XL minus XC whole square. So as you can see in the diagram, R value is given, L value is given, C value is given, but XL value is not given, XC value is not given. But in case of impedance equation, there we need XL and XC. So basically, first of all, from the L value, from the value of L, we have to find out XL. From the value of c we have to find out the xc. So solution, come to the solution. So first find the xc and xl. As you can see, so xc formula already I have discussed, that is 1 by 2 pi fc. So put the values. xl, that is again 2 pi fl, so put the values, we will get the answer. Okay, so net reactance is the difference between these two. Now you can ask me always why in the equation xl is higher, placed before of xc. So it is not such thing. So in generality it has been seen that xl value is higher at our Indian standard frequency. So that's why it is placed before of xc. But you can put the reverse case also. See, as you can see, there is a mod. So mod means which one is the higher, that result will be positive. Maybe any one is the higher one, xl or xc, but the result must be positive. That's why there is a mod value. So the total reactance is given by the mod of xl minus xc. So we will get some um, net reactance value. Now if xl minus xc is there, if xl is higher than xc, then the net reactance is inductive in nature. If the reverse case happens, xc minus xl, then the reactance is capacitive in nature. So now what is so now we know r is already given in the problem. Next one is the from L we have find it out xl, from c we have find it out xc. Now we have to find out the z. So in which form we have to find out the z? In rectangular form, in the polar form. So first, so as you can follow my pointer, the impedance in rectangular form, that is the equation that we have discussed 2-3 minutes before, that is z is equal to r plus jxl minus jxc. So only thing what we have to do is that to put the values. So what is the value? R value is given 5.6. Follow my pointer. So z is equal to r plus jxl minus jxc, that is equal to 5.6 ohm plus j 6.28 kilo ohm minus j 3.39 kilo ohm. So all components are in kilo ohm. So we have placed those value, and z is equal to ultimate result is 5.6 ohm plus j 2.89 kilo ohm. So now if we want to find out this rectangular impedance value in the polar form, so we know the equation already, we have discussed, that is the z is equal to under root r square plus xl minus xc whole square into tan inverse z net reactance by r. So if we know the values, yes, we already know the values, so we can plot those values over there. So if we plot those values over there, so what we will get, R value is 5.6 kilo ohm square plus net reactance value. What is the net reactance value? 2.89 kilo ohm. So make it square, and there is a tan inverse. Then is a net reactance 2.89 by the resistance value, that is 5.6. So whatever value is will get, that is the magnitude, that is the angle. So rectangular means x plus jy format, and rectangular and polar form means there is a magnitude r theta format. Actually it is known as the r theta format, that is a magnitude, and with that there is a angle. So now like this way we solve this kind of problem. So that means what we have to take into the mind, that is, okay, we have to solve the problem. Okay, what we have to find out, that first of all we have to check. After finding out that, then what are the for finding out that particular result, which equation we need to know. In that equation, which values are given, which values are not given. If some values are not given, then those values how to find out. Those are the steps how we can very easily and tactfully we can handle any mathematical problem. Maybe easier, maybe harder, oh, all are same. So we have to just rethink how to proceed for a particular engineering problem. Okay, this is a simpler problem, already we have discussed. Now coming to the next problem. Yes, analysis of, this is a very important topic. So analysis of series RLC circuit. So what is written, first check what is written over there, then I'm going to going to explain you everything. So recall that capacitive reactance varies inversely with frequency. Already discussed, that is Xc. Xc is changing inversely with the frequency, and inductive reactance, that is Xl, is directly changing with the frequency. In this section, the combined effect of the reactance as a function of frequency are examined. That means that net reactance. We are here just discussing about the net reactance. Net reactance, I already have told, that is the XL minus XC or XC minus XL, whatever. It depends upon the values, but as there is a mod, so always the result will be positive one. So now very interestingly come to the diagram. So in the diagram, in the x-axis we have the frequency, and y-axis we have the reactance. Okay, now just check, here there is a dotted lines and there is a curve. So this blue curve is showing us the inverse effect, inverse relation between frequency and the Xc. So that's why it is like this inverse relation, and XL is had direct relation, that is directly proportional with the frequency. That's why when frequency is increasing, so follow my pointer, in the x-axis we have frequency from 0 value, it is increasing. So definitely what will happen, the XL value is definitely increasing. So if we plot like this, it will come like this green line, it is a straight line. But in case of XC, it is not straight line, because it has the inverse relation with the frequency. Now very important point is there, that in this particular graphical analysis we can say that there is a XC curve, there is a XL curve. So it is intersecting somewhere, and at that somewhere place it is known as the resonating frequency, where the value of XL and XC is magnitude is same but the direction is opposite. Okay, so we will discuss in later class about these things, resonance, series resonance, parallel resonance, different things are there. So for now, just follow. See, before resonance capacitive, the total reactance value, the net reactance value, it is a capacitive. See this section, and after resonance, this is inductive value. Yes, this is the thing. So series, this is the concept actually, how we can think about the properties are changing with respect to the frequency, because this Xc and XL both are the frequency dependent quantity. And in case of, see, from this point you can very good understand, you should have this very good understanding regarding the DC circuit, where, see, DC circuit doesn't have any frequency. If it doesn't have any frequency, so there will be no existence of XL and XC. So in case of DC circuit, total impedance is equal to, then it will be R. So that's why in case of DC circuit, there will only exist R. Okay, so yes, coming to the next problem. So let us say what we have to find out in this particular problem. So let us just read out what is written over here. For each of the following input frequencies, so that okay, find the impedance in polar form of the circuit in figure 18.4. Note the change in magnitude and phase angle with frequency. Okay, that means there is a circuit, RLC circuit, and in that RLC circuit different levels of frequencies are given, and for those different frequencies, what is the impedance value, that thing we have to find out. See, before starting this particular problem, I just view, just check the problem. So in the problem, 4 frequencies are given: 1, 2, 3.5 and 5. So that means the frequency is increasing. So with the increasing value of frequency, how the impedance is changing, and this impedance changing depends upon how the XL and X is changing, because both are frequency dependent quantity. So if the frequency is changing, this XL and XC, both component values will be changed, but resistance value will remain fixed. Correct? So going to the solve. So first frequency is 1 kilohertz. So at 1 kilohertz, XL value is the equation is there, XC equation is there. XC equation is given by 1 by 2 pi FC, and XL is 1 by, sorry, XL is equal to 2 pi FL. So put the value, we will get the XL and XC value, then put that value in the impedance equation. So as we can see, follow my pointer. So this is the Z equation in polar form. So after putting the value, we have get 8.04 at an angle minus 65.8. Now in the previous problem we have seen that there is a positive angle, there is a negative angle. That means what? It is at a leading power factor. Okay, so now at frequency 2, the same things we are repeating. Not, it is not a harder problem, it is the easier problem. Just see here, just see, when the frequency is changed from 1 kilohertz, it is to the 2 kilohertz. So there what you can see, we can see that again they have find it out XL and XC value. Put that XL and XC value in the polar form of the impedance equation, and there from there we have find it out the value of 4.28 at an angle minus 39.5 degree. Like this, where 3.5 we have placed, so the value is 3.3 angle minus 1.22 degree kilo. And when it is plot 5, so 5 kilohertz, so in that time, see, the value is 3.65 and angle is now in positive domain. See what is the angle? 25.2 degree. So just visualize, with the change of the frequency, the magnitude of the impedance, the angle of the impedance, phase angle of the impedance is, it is changing. And when it is changing from 1 kilohertz to 5 kilohertz, so we have seen the scenario that here the value of the from the when the frequency value is increasing, the impedance value is magnitude is decreasing, and the power factor is changing from leading power factor to lagging power factor. So like this way, the impedance and the phase angles are changing. So like this way we can solve any kind of problem. So very importantly, we have to understand that what is the nature, what is the behavior of this AC circuits, how they behave, how 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 they react, how, what are the characteristics it has. So those things we have to very understand. Already we have discussed in the previous classes. So in this particular class we have solved some problems. Okay, so one very thing, so two problems already we have solved. So two things I want to show you. Okay, yes, see the diagram 18.185. The voltage across the series combination of RLC is always the larger individual one. So what I have already, we have already discussed that thing. Here it is pictorially shown for the better understanding for you. See, there are the 3 voltmeters. So one voltmeter is connected across the capacitor, one voltmeter is connected across the inductor, and 1 voltmeter is connected across the both R L combination. So as in the scaling section, follow my pointer. In this is the scaling section, scaling. This is the scaling section. So as you can see, so in case of VC, the voltage across the capacitor, it is this amount. In case of VL, the voltage across the inductor is this amount. But when you are considering both, so it is the difference between these two. It has this value minus it has this value. Whatever is the difference, that value we are getting over here. So this is the difference value. So the point what we have already discussed, that is the voltage across the series combination of C and L is always less than the larger individual voltage. Okay, so like this way, so this is the pictorial representation, and this is the last thing, that is the waveform analysis of the of that same thing. So what is there, as we can see, um, So there is this red one is the VC and this blue one is the VL, and combining these two is the green one. See, it has opposite nature with respect to this VL, and the combining these two has a different characteristic, different magnitude. So this that means when we are considering our LC circuit, RLC circuit, that means that at that time, so the phase angle must not be 90-degree, because it is not a pure inductive circuit or pure capacitive circuit. That's some ins phase angle. So that thing we can calculate. So formula is already known to us, tan inverse um, net reactance by R. So that is the formula. That from there we can find out the phase angle between them. So this is all for today. So in this particular class we have seen that RLC circuits is behavior and different problems regarding that. So I think you have understand, and in the previous class also we are going to discuss different problems regarding this. Okay, thank you.